Okay, so here you have an example of an electron transition problem for a hydrogen atom. So the question asks us to find the wavelength of light that is emitted when an electron moves from N3 to N2. So on the right here, you have the energy level for hydrogen, and it says N3 to N2. So let's go ahead and box the energy associated with this particular problem. So I went ahead and boxed N3, which is 1.51 eV. And then the energy associated with N2 is 3.4 eV. The negative sign here simply implies that it is binding. Okay, so but for this stuff, you can just kind of ignore those values because you're just trying to find the wavelength anyways, which is the magnitude of things. So here, in order to find the difference in energy, how much energy is emitted, you can simply take the final energy minus the initial. But you notice here in my work, again, I decided to leave out the negative sign because I don't really particularly care for it. I just need to find how much energy is either given off or absorbed, but the value stays the same, whether it's a positive value or the negative value, whether you're going from N3 to 2, 2 to 3. So in this case, if you're going from N3 to N2, you give off 1.8 eV, but therefore the opposite is true. If you want to go from N2 to N3, you would have to absorb the same amount. Okay, so whether it's negative or positive, that depends on the wording of the problem, emitted or absorbed. But here I like to just use the value and just take the difference so I know how much it is. All right, so once I know how the energy difference in the two energy level, I can just convert EV to joules, and the conversion factor to go from electron volts here to joules is given in Planck's constant up at the very top of the screen. There's 1 EV. 1 EV is equal to 1.6 times 10 to the negative 19 joules. So that's where this conversion factor that I'm circling on the screen comes from. So again, I went ahead and start with 1.89 EV, which is I found in the previous step, and then you need to convert it to joules. And if you do that properly in your calculator, you should get 3.024 times 10 to the negative 19 joules. Now that you have this stuff in joules, you need to apply the function E is equal to HF. And here we know E, we just found it in joules. We know H Planck's constant. We want to use this very last variation here because it has units in joules, which matches what our unit is for energy. And the only thing missing is for frequency. So to find frequency, we just simply divide both sides by Planck's constant. So that looks like frequency is equal to E over H. E we found in the previous step, which is 3.024 times 10 to the 19 joules. We just carry that down. And now for Planck's constant, you have to know which one to use. In this case, we want to use the very, very last statement there of 6.63 times 10 to the negative 34 joules times seconds, because it will permit us to cancel out joules, and that'll leave us with units of seconds in the denominator. But S in the denominator can be rewritten as S to the negative 1, but S to the negative 1 is the same thing as 8 hertz. So you notice here, I'm just changing things so that it looks proper. So instead of leaving S in the denominator, we want to rewrite it as S to negative 1, but you got to recognize that S to negative 1 is the same thing as 8 hertz. So really the same values, just now with different unit notation. Okay, but now that we have frequency, we can find wavelength simply applying the wave speed function. The wave speed is equal to lambda times frequency. To find lambda, let's go ahead and divide both sides by frequency first. And then here, we know what the wave speed is for this particular unit. Or the wave speed would simply be the speed of light in a vacuum. So therefore, V is really your C constant, which is 3.0 times 10 to the 8th meters per second. We just found frequency. So let's go ahead and plug and chuck those two values in. So here in the numerator, I have the constant for the speed of light in a vacuum of 3.0 times 10 to the 8th meters per second. And I carry my frequency from the previous step down, which is 4.56 times 10 to the 14 hertz. And if we do that, the units for seconds, aka hertz, will cancel out. And the only unit left is the unit for meters. So if you punch in your calculator, you should get a value of 6.57 times 10 to the negative 7 meters, which is the same if you convert. It'll be 657 nanometers. So be careful whether the question asks you for units in meters or nanometers. Here, I've chosen to leave it in just meters. But again, if you want to convert it to nanometers, it would simply be just 657 nanometers. Okay, so that's your answer. So here, I have a diagram for you. It shows that if an electron transitions from N3 down to N2, according to Bohr's model, it should release a wavelength of 157 nanometers, okay, which is equivalent to the color red. All right, I hope that helps. And that, stay nerdy, don't be whack.